that I'm going to present today is about the challenges and the opportunities in big data in healthcare informatics. So I'm going to talk about what are the enablers of making big data successful in healthcare. What are the challenges, the barriers, and mainly we're talking about semantic interoperability of data in healthcare and how we address these problems. So the objective is to have an overview of some of the healthcare problems in terms of cost, process, data, and then have some understanding of how the semantic web can help us enable big data analytics in healthcare. And then I'll put some use cases, one big use case that we are working on in our research lab related to clinical pathways in healthcare. So we'll follow this outline. And I'll start with the motivations, the problems, research challenges, and the goals. It's very important to understand the problems and the research challenges of any type of research so that you can value the opportunities in terms of those young researchers who want to invest in this area. So in healthcare, the problem of healthcare is the cost. And the cost of healthcare in the US, for example, is at $3.5 trillion a year. So we're talking about $3,500 billion that America in the US spends on healthcare every year. And that represents around 20% of the GDP in terms of spending. And this huge amount of money that is spent in healthcare, 30 to 40% of it is overhead. What does it mean, overhead? Overhead means that this is the amount of money that is spent into the support of healthcare. It doesn't go to the payroll of those physicians, nurses, technologists who are taking care of the patient. So anything that is not directly going to the patient is overhead. The support, the technology, the admin, the infrastructure. I'm not talking about the medical infrastructure, but the other infrastructure that supports it. So 30 to 40% of $3.5 trillion, we're talking about here almost $1 trillion, which is $1,000 billion in the US. So any saving in this amount of money, from this amount of money, is going to help us reduce the cost and enable the government to take care, to pull more money towards the patient health instead of the support technology. So if we can reduce that 30 to 40% by 10%, which means that we are saving $300 billion to the government, to the US. In Canada, it's almost the same. We have 10% of their population. We have 30 million people in Canada. So we're spending something like $280 billion. And in mental health, for example, in Canada, we spend $40 billion a year on mental health. Just imagine the amount of money. So the cost is a disaster. And this is the problem with most of the countries. Most of the countries are having problems to cover healthcare. And the process also is not right. The current processes mostly is no evidence-based type of care, which means that it relies on the experience of the physicians, the way they do things, the way they learn how to treat patients and so on. We are not making use of the data. So out of the data that we have on paper in the files, maybe we are using 30% of that data, which is only the data that is prescribed in the EMR, the electronic medical records and EHR systems. So poor communication and collaboration between the teams and all kind of poor prevention mechanisms because we don't have the teams working together to prevent the diseases from from controlling them and so on. The IT also is suffering. So you go to a hospital, you find that they use more than sometimes 4 or 5 different information systems. They belong to different vendors. And these vendors, they are coming with their own data, standards, formats, and so on. And therefore, the system, they don't talk to each other. And therefore, we cannot make use of the data that we have. And various EMR systems have different, as I said, different formats and so on. Also social implications. Because of all these problems which are related to the organization, to the data, to the vendors, to the IT infrastructure, we have issues with errors because we are not dealing with one system. The data is not structured. Most of it's free text in natural language processing, which is what the doctor are prescribing in your file. And therefore, there are a lot of errors. And those errors are the third leading cause of death in the US, with more than 250,000 people are dying because of errors, either in prescriptions or maybe we did not track their history properly and so on. So all of these problems are due to one major thing, is that we are not making use of the data that we have. And therefore, we don't have control over the process of healthcare. So we need to do some changes. So we require some changes, and those changes, the changes that we need is in the way the healthcare is delivered, medical data is used and shared, medical knowledge is managed and transferred. So a lot of good practices are happening. A lot of great teams in healthcare are doing great things. But that knowledge is not transferred to other places. So what we call translational medicine is suffering. Why? Because that knowledge is on paper. That knowledge is within closed doors, is within those teams. So people cannot get that knowledge from the systems on the web. And therefore, we are not propagating the best practices with those that are related, that are based on evidence. So how to use IT to propagate that knowledge, to make it public? Like, for example, now everybody can go on the web and they learn anything. So everything is on the web. But if you want to go on the web and learn how to treat a disease, you hardly find something which is reliable and it is approved. So we want to use big data analytics and other AI technologies so that we encode knowledge the same day we encode data, and we allow people to share it through the web. And that's what comes, these are some of the challenges that I was talking about. So what you see on the left-hand side here is all kind of problems that is related to data. Data is fragmented, coming from different systems. It's missing data. Sometimes the formats and the standard that we use are different than formats and standards that are used in other countries or other hospitals in the same city sometimes, and so on. So, and these problems on the left-hand side, of course, they impact the processes. The processes also are suffering. Complex decision-making and changing knowledge, medical errors, inefficient workflow, and so on. So, and here in healthcare, we are talking about a large amount of data. So people who have done some research on data in healthcare, they believe that the data that doctors are generating every day, which means that the data that they are writing on their patient files, it's much more than the data that is generated from online shopping, banking systems, insurance companies together, so worldwide. So here we are talking about high volume of data. And the data that is changing every day. The patient today in the morning is different than the patient state in the afternoon and tomorrow. So the data, the same type of data is changing, is kept updated and so on. So the velocity of the data is a high velocity, which means that there is a dynamic in the data that you need to capture and properly and to track and then to timestamp it. Also, the type of data. So you have data related to the questionnaire when you go and see the doctor. So he will ask you questions and he tries to prescribe what is your temperature, what is the problem. And there are some data that is coming from the labs, imaging labs. If he asks you to take a CT scan or X-ray, there are information that is coming from labs. And there are different types of test labs that they may ask you for. So we have different types of data, and this data is complex, and it's encoded in a different way from one practice to another, from one country to another. So in order to allow all these institutions to make use of this knowledge, So we have a problem of standardizing the data, allowing people to use more or less the same format, although it's impossible to ask everybody to use the same format, but at least to use certain formats that we can map. We can do some semantic matching. So we have all the problems that we have on the left-hand side are the problems that big data is dealing with. Okay, so big data is about high volume of data, high velocity, different variety of data. And what we want to do, we want to process it using different types of technologies and mainly deep learning in order to get some insights. So we want to identify some patterns, learn from the data, learn maybe from the processes of treatment and so on. So, and here I'm giving you here just the kind of data to see the size, the volume, and so on. If we are talking about medical images, we're talking about petabytes. So that's a huge amount of data. So to store and to process. So we really, the big data there's opportunity to use big data and make a lot of saving. But the problem in healthcare that the information is not cleaned. The data is not clean. The data is not linked. We're talking about unstructured data. So we have to use a lot of natural language processing techniques and other kind of techniques in order to start using big data, which means that the data that we have in healthcare is not ready to be used by big data analytics, except the imaging one. So in big data analysis, you can put images, and then those images with deep learning, you can train the images and so on. You do the training and then know those who have, for example, present some type of cancers and so on. Apart from the imaging, the other data is unstructured data, and you need all of it in order to be able to get some big data analytics in an efficient way. So therefore, we need to involve semantic web technologies here in order to do that. This is here just the pyramid of to show you the amount of data. We have some private data, public data at the bottom, and this data, it needs to be cleaned and collected first, cleaned, linked. Then after that, we need to do some information retrieval on it, and then from there we can go up to the hierarchy at the top where we can apply some big data analytics techniques and so on. So stage one. This is the pyramid for all kinds of big data, okay? But in order to look at the healthcare, stage one in healthcare is different than stage one in big data for finance or big data for shopping, for online shopping and so on, where the data is structured. So you're talking about the customer, what are the items that he bought, or if it is a customer in finance, what are his transactions? Someone has bought some shares and so on, and we can feed that data. It's clean, the code for the shares is there and so on, and it's easy, we can do some data analytics. In healthcare, the data is coming from different places, as I mentioned earlier. Most of it is different format, especially the most challenging one is the free text. So we need to do a lot of cleaning and so on. So here we're showing a little bit the traditional steps of any knowledge discovery process. And the thing that I'm going to talking about is the first and the second stage. Is about the selection, the linking, and the pre-processing of the healthcare data. So, and semantic web technology is important and has been proven to be the most appropriate technology to deal with this. And the health data is, as I mentioned, is quickly increasing in size and so on. Therefore, and the other problem also with health data, in health informatics in general, is that the biological sciences, which are the science of the genomic and so on, DNA structures and so on, plus the science of translational medicine, the way the medical doctors, they are trained and so on these sciences and so on, plus the healthcare practices, the way we treat diseases, we diagnose them and we treat them and we follow up with the patients. All these sciences, they are interrelated. And then you cannot rely on something and then forget the other piece. And therefore, you need to, the semantic web will be the perfect tool, to link the fragments of information that are coming from the different domains in order to support efficient decision taking. So, semantic web is an interoperability technology. It's been designed to allow communities to talk the same language, So it's about ontology. Ontology is the way we It's not coming from here because I switched that and still doing it. I think I have a loud voice, so maybe the people can hear me. So while you are working on this, so I can continue. So, yeah, I think they can manage to hear me anyway. So the problem, as I said, semantic technology is that it allows to. The semantic web is there to define knowledge domains, okay? And then define them in a formal way so that we can apply some reasoning and processing, which means that we can computerize, we can apply processes in a formal way. We can define knowledge domains in a non-ambiguous way. And it's supported by certain standards that we use, and it's all about interoperability. It's based on XML. And on the top of XML, we have RDF, the Resource Description Framework. Then we have the OWL, which is the Web Ontology languages. Then we have a schema that allows these ontology languages to be used by web services on the web. And then we have other type of semantic web rule languages to allow to do some reasoning. And then we have the RIF and so on. So all these technologies are there to allow machines that talk different technologies and standards, and they are developed using different programming languages to talk to each other nicely because it's all based on XML. So, and this is the outcome of what we want. For example, here we are sharing, we were showing some semantic web links, the LOD, linked open data in healthcare, where we are sharing information about the genomics and information about the clinical information. So this is what we want to do with the data in healthcare. We want to generate something like this. But in order to get to this, we have to go through a number of stages. So what are the challenges? The challenges is convergence in technology. So we want all the technologies to adopt a little bit the semantic web, and then to be able to share, at least to adopt the standards and the format so that they can talk to each other, these technologies can talk to each other and exchange information and so on. So also we are dealing with, as I mentioned earlier, integration of multiple data sources, data coming from different places. And we need a unified data map and ontology as a point of reference, and I will explain this a little bit later. So we need also to develop some data modeling and data exchange mechanisms. It's not about just data, but it's also about the processes. We need also to capture the processes, which are the events, and how the data is related to the event. When you say, I want an X-ray, so here you are talking about an event. You are asking for an ordering, what we call in medical terms, you are making an order, a medical order. And that medical order is going to link it to the data, which is the details of the radiologist that he's going to see that X-ray. And so we have the image, the report, and the order. And all of these is time-stamped. So that when you ask for another X-ray next day or in the afternoon, you can see a little bit the progress. You see the dynamic in terms of the data of the first one and the second one, the third one. And here we're not only talking about data of the same nature. So I want to see the X-ray, then I want to see the CT scan, I want to see the lab test, and I want to correlate all of this data and try to make sense of it. So what we are trying to do, we are trying to do it on the machine. Therefore, we are the big data. So it's easy to find out the big data algorithms because they are there in deep learning and so on. But the deep data will only give you a good result if you give it the right data. So we are here working on the kind of data and how the data, what data you have to use in order to feed that big data analysis model. So, and in healthcare research, big data, the decision makers are after two things. So we have, the first thing is preventive medicine, and the second one, which is the most important, is the predictive medicine. Preventive medicine is what we do every day in our research in terms of healthcare, is how we can prevent prevent from diseases to happen and so on. And it's about what happened. So you try to understand, there is a pandemic in terms of a disease, you want to understand what happened. So you collect the data and you try to analyze it to understand what happened. And here we use a little bit the data mining techniques. And then you need to answer, why did it happen? So how that we couldn't prevent it, okay? And here we're talking about the patterns, the descriptive analytics techniques that we use. But the move in terms of research in healthcare is not to wait until it happens to understand why it happens, but to prevent it, to predict it before it happens. And that's the second part, is predictive medicine. And that's what the long-term research is targeting, is what could happen. So you try to forecast in the future. So, and then if you understand what could happen, then you can put all the resources so that it doesn't happen. So, and that's what should we do in terms that it doesn't happen. And here we use predictive analytics techniques and the prescriptive analytics techniques. So how we can get there? So usually the steps of collecting the data and cleaning it, so all the data needs to be digitized, that's obvious. And now, for example, in the US and Canada, sorry, I use these two examples because I'm coming from Canada, but I'm pretty sure in other countries also they have a good, similar type of rates. 90% of this, of adoption in the EMR, which means most of the data is encoded in the EMR and so on. But unfortunately, some of the data is a free text. And therefore, even if it is there, we are not making use of it because we don't have yet intelligent natural language tools that allows us to pick the right data or to pick the right concepts and information and link them from that free text. And the second step is what we call the technical interoperability is a bit challenging from the policymakers, is privacy and security that allows a system not to share data with another system. So, and in healthcare, we have this problem. Every time you want to do a project, you apply for a grant, you have to wait 6 months for the ethical committee to approve it. Why? Because they are afraid of privacy and security. And they tell you that, okay, so we want to make sure that the technology that you are using is anonymous, and therefore we are not treating ourselves for legal aspects and so on. So that's what we call technical interoperability, is the fact that a system is sending data to another system. Okay, so, and then the third and the most difficult one, which is the semantic one, the semantic interoperability, is that an application on this computer is talking to an application on the computer, and they are not only sharing data, but they are also using this data without each other's consents, without negotiating with this, which means that if I receive a data receiver in one application receives data from the other one, so he will understand the format, the purpose, and of that data, and then you can apply some big data analytics or all the type of processing on that data without negotiating with the sender. And that's what the most difficult one. So, and that's the definition that I was talking about at the top. So this step is the most challenging one, and it's referred in semantic web, in healthcare as the semantic gap in terms of healthcare. And this is the transition from technical interoperability to semantic interoperability to clinical intelligence. Clinical intelligence is done with big data analytics and other AI techniques, but the semantic interoperability, if the data is not semantically correct, cleaned, processed and cleaned, then you cannot do much with it at the clinical intelligence stage. So the healthcare semantic interoperability challenges are, just to give you an example, for example, just to describe that the patient had got heart failure, some researchers have done some statistics and they found that we use 91 different codes using 3 different standards. SNOMED CT, ICD-10, ICD-9 are different standards. Some hospitals, they use SNOMED CT, the others, they use ICD-10, and the others, they use ICD-9. And these guys, in order to describe, just to say that to describe a guy with a high heart failure, they use 91 different codes. So, and in healthcare, clinicians, they use thousands of codes. Many of them are overlapping. They say the same thing. Or if they don't say the same thing, people maybe they are confused and they may think that they are talking about the same thing. So we need to solve all these problems of interpreting in order to do some big data, meaningful big data analytics. So the technology that you use to do this is ontology in order to have, for example, to match a certain terminology used in one hospital with another one. So we encode this knowledge using ontologies and this knowledge using another ontology. And then we need, of course, in order to make use of all the experiences, we need someone, the middleman, to learn from the two experiences. Therefore, we need to do some matching between these ontologies. So we have this ontology merging, matching, alignment, which is a big issue in terms of research. The way knowledge representation, the best way to represent knowledge and related ontologies, how we share knowledge. When I say share knowledge, is the business logic. You know, in a system, you have your data, and then you apply business logic on the data. So that business logic needs to be taken and given to another computer, an application, as a web service to use it. So not to use the outcome of that, but to use the business logic which is encoded. So which means that the knowledge should be also encoded in XML and made available to other parties, which could be other applications, to use it. So that's what we call knowledge sharing. And we use the RIF technology for that. Knowledge revision and consistency, because things are changing dynamically in healthcare. We need to have a mechanism to update this knowledge and say, this is not valid, this is the way we do things now, and so on. And then to do the analysis and reasoning, which is the paramount stuff for doing the treatment of. So this is the technology. I will not spend a lot of time here because we are restricted in time. So these are the technology that we use in order to encode this knowledge, data, link it, and so on. So we have the standard markup, semantic markup languages, which is XML. Everybody maybe is aware of XML. Allows the machines to talk, to exchange data. And heterogeneous machines to exchange data. We have then RDF, the resource description framework, is to be able to encode very small facts, for example. So I published my web page. So this is the triple. So I'm talking about myself, and then I'm publishing the web page. That's my web page, and then the action is publishing. So that's a triple. And that triple is installed, is encoded with RDF, and it is published on the web. And every single entity that we use will have a UDI, and that UDI is uniquely identified on the web. So all the concepts, the facts, the processes are also encoded in RDF and so on. Then we have RDF schema, is the ability to have web services to use this data properly and to make sense of it, and the web ontology languages to describe the ontologies, and also to have the ontologies available for web services to use, the WS and so on. And then we have the markup languages, which is that the tools that allow us to process this knowledge on the web, regardless of the technology. Rule ML and semantic web rule languages. And then at the bottom, we have, those are the web services and the web agents that we use for different purposes. And then context awareness is very important, because in healthcare, everything is related to a context. And then you have this data, you can use it for one context, you can use it for second context, the third context. So you have to define the context and so on. And in fact, in this area, people cannot work on their own, although you have research teams working in very, very narrow topics, but it is a multidisciplinary type of research where it's a convolution between semantic web, artificial intelligence, IoT, because a lot of data is coming from now, sensory data coming from in the hospital from different machines and so on. The cloud, that's where we store the data and the processes. Although the cloud there's an issue with the cloud in healthcare. A lot of institutions are afraid of using the cloud, except if it is a private cloud, because of the privacy and security. And then we have the open standards like SNOMED CT, ICD-9, CD10, and so on, which are very, very well developed in healthcare and so on. So for the semantic web ingredients, So the challenges or the research challenges are how we annotate very well the resources. The resources is this data, the processes, and so on. So because the content is very important. Then there are some also research on the semantic markup and reasoning. So how we deal with web resources coming from different sources, how we can link them, and then how we can ontologies to allow people to share them. And then we have the powerful semantic querying, how we query this information. And then we use a Sparkle, which is like the SQL for the web, for the semantic web, to query like you are querying a database. So, and then we have the open standards, which allow institutions to encode data based on these standards so that they facilitate a little bit the task. And then we have also the problems with the cognitive semantic web is how we get these agents and reasoning tools to manipulate the knowledge and share it. So these are, I already did talk about this, these are the tools, and they are very well-known tools. And this is an example of what we're trying to do here. It's the, here we are showing how the data coming from an EMR is, which is the EMR, the electronic medical record, is linked to data coming from the LIMS, okay, for the genomic data about the DNA of the patient, and what kind of linking we have to do and what kind of processing we have to apply on this. And then here I'm showing how RDF allows you to show the semantic links between these elements and the causalities between a patient's state and his DNA test and so on. And here, this is the formal definition of an ontology, which is that a formal way of specifying a knowledge in a very specific domain. And when we say formal way, which means that we can apply some processing and reasoning. So it's a machine processable type of knowledge, and so on. And who's going to use it? We'll have multiple parties, devices, applications in IoT, web agents, people, machines, and so on. So all of these are, this is the ontology. What kind of ontologies we use in healthcare? So we use what we call domain ontologies. They allow you to express knowledge about a specific domain. We're talking about, for example, the genomics, the clinical pathways in stroke, for example, pathologies and the way they are treated in cardiology and so on. And then also we have ontologies for big data processing. They tell you, okay, what type of data mining you have to upload, you have to use, define the knowledge about the data mining, the process, its steps, and so on. So we can even share the way we do data mining on a specific applications, on specific data, and we make that information available to all the processes to use it, so that we can compose processes and so on. And then the most important one is the metadata ontology. It defines you, it tells you that if you want to ask this question, let's say I'm asking questions, for example, a specific question about a disease. What makes that disease propagate in this period of time? So I have the word disease, so I go to the ontology of that disease, and then from that ontology, in that ontology it tells you that disease could be due to this and this and this, and this is the type of information that we use in order to diagnose that disease. So this will be an input to get the data that you are after. So this ontology, what we call the metadata ontology, allow you to select the data that you are after. Then you can go and take that data. That data is also linked in the ontologies, and then you can prepare it for big data analytics. So the thing that the ultimate goal, which is not yet achieved now, is robots, agents, that will receive your question, and then they will go learn about what that domain, what the question is all about, gather the data that they think is appropriate to treat or to answer that question, and then go and get that data, prepare it in a format that is the format that is known format for the big data analysis, which is the array of those numbers or whatever, the logical data and semantic and so on, and then feed it to a deep learning type of machine to answer or to get some insight about the pattern or to have an understanding of why we have this problem. So we have different type of ontologies for that, and this is the knowledge where we get the data from, the knowledge from, sorry. We have what we call operational knowledge and domain knowledge. I did talk about domain knowledge. Domain knowledge is about the things that are static. They don't change quite often. They don't change every day. So this is the way we treat, for example, this is the way we describe a disease, the way it develops. This is the genetics. This is the genomic of certain diseases, DNAs and so on, and so on. So here is what the doctors learn from the books or when they are at med school. Okay, so we encode it, that's the bottom part. But without the top part, which is the operational knowledge, the way we use that knowledge in the practice. So imagine you have someone who has a stroke and is also diabetes. So stroke and diabetes, and he's coming. So you need to learn about both, okay? So usually you get a physician from the diabetic department coming, and then you have a person from neurology coming. And these two guys, each of them has his own knowledge from the bottom, but we need to give them ways to share that knowledge into how we encode that shared knowledge into the system so that we can some support systems that allow them to take that decision making effectively. So here we're talking about things that change every day. Patient ontology, clinical pathway ontologies, service functionality ontologies, service message ontology. And I will give an example of these ontologies. Oh, sorry for for the first one. First one is just a very basic ontology for a patient. Here we're talking about an ontology for the way a hospital is organized. So for example, CARE, consult patient referral, observation reporting, scheduling department, patient referrals, and so on. So, and then we have here an ontology that is talking about the messages. The messages is when I send someone for X-ray or PET scan or CT scan or lab, so we use codes. So, and those codes, we need to encode them into the system so that the system, when they see those codes, he can refer to the data that we are after. So this is an ontology that shows a little bit those messages. And here, drug ontology, that there is the drugs, their how they are prescribed, their contraindications, and so on. So here, these are some standards that the healthcare institutions are very good at writing standards because they find them are a way of sharing knowledge. So all of these standards, they exist and they are adopted and so on. And here are how we put things together. And then I'm showing a little bit how we can exchange information about genes, diagnoses, drugs, procedures, and so on. I'm showing both the semantic and the syntactic interoperability issues. Semantic is related to the data, and the syntax is related to the processes to do that. So in the last part, I will show a little bit some of the work that we're doing about clinical pathways. What are clinical pathways? Clinical pathways are the way we implement guidelines in a hospital. For example, we say for stroke, we are focusing on ischemic stroke in our research. And then they say, you learn about, doctors, they learn in school about how to diagnose and how to treat clinical ischemic stroke. But in the hospital, when they get to the hospital, they have to apply that knowledge in a different way. When I say a different way, depending on the resources. I'll give an example. You have two hospitals. One, and we're talking about the neurological department. So this is neurology with 40 doctors and nurses and so on. Another small neurology department with 20 people. So this number of resources here is more than resources here. For sure, in this department, people will do small jobs because they are specialized, because they have other people to do the other type of check. But when you're in a small department with 20 people, the people, they do a lot of stuff because they don't have people to rely on. Okay, so the clinical pathways is the business model of practicing medicine on the ground, which means that it takes into consideration the resources, the human resources, as well as the best practices that are applied. So what we did, we encoded the clinical pathways using ontologies, which means that we represented formally the way clinics work and practice. And we try to link all the data they need in order to apply some big data analytics and allow them to make use of the knowledge they have used and the data they have used to learn from it and so on. So it's a way to allow medical teams to work together So it's about documenting in the way they work. If they work together individually, they do that. If they work together, they have to share the documentation. So clinical pathways, so they are documented using, as I said, they are represented using pathology, using ontologies, and they allow you to take. So this is like an example of a clinical pathway, which means that in order to treat a patient with a disease, there are different ways of doing it based on his case. If he's presenting this type of symptoms, we go one way. If he's presenting other type of symptom, we go the other way, and so on. So, and this is the way it's done on paper. Doctors now, they have this chart, and then they follow the chart. Okay, I have a patient, I diagnosed him with stroke, he's at this stage. So next step I go to, it's a flow chart, I go to the second stage. So in order to move from this to a computerized system, so we created these ontologies. Another ontology, they tell you, okay, day one, do this action, day two, this action, and so on. Here, imagine that we have two departments. One is using CP1, clinical pathway 1. The other one, they do it in a different way, clinical pathway 2. How we can combine these clinical pathways or share this knowledge from the two different sources. So when we share, we will see that we may end up with duplicate tests, duplicate actions, and so on. So here we're talking about an example of ontology merging and so on. 5 minutes? Yeah, I'll be done. Yeah, thanks. And since the way we treat patient is related, is a time constant, is related to time, so most of the question is that how long did it took us to move with the patient from stage 1 to stage 2? Why? Because this is related to cost. Every single day the patient spends at the hospital are thousands of dollars that you are spending. So if there is a team in another hospital who can take a patient from stage 1 to stage 2 in 3 days, rather than 5 days, that's what we are doing here, then it's good to learn what they are doing. What we are missing in the process, how they are making it. But it doesn't have to be on the cost of quality of service. So the quality of service needs to be there because these clinical pathways are generated by institutions and they are shared. They're supposed to be the best practices, the best guidelines, and so on. So it's very important that we capture time in these CPs. Okay. So for that we use the time ontology. The time ontology exists, and then we incorporated it. This is the time ontology. We incorporated it with our ischemic stroke clinical pathway ontology, and we were able to capture all kinds of questions related to time. So if the doctors ask about, it's not about the patient they are treating, because they know about the patient that he's there and then they have seen him for 3 days. But if after 6 months, I want to go back in the past and then pick thousands of patients that we treated, not only in my hospital, but in different hospitals, and here is the Department of Healthcare at the regional maybe or the provincial side, and they want to learn how much resources we spend on ischemic stroke for critical cases, then our system should be able to mine this data because we linked it properly, and then we'll give them all kind of time constraint checks. So how we do that? So we need to use international standards. So we're using SNOMED-CT. SNOMED-CT is terminology and encoding that the hospitals that we are used at the hospitals, which means every single symptom, term, procedures is given a code. And then these codes, and then we're showing some metrics related to conformance of these clinical pathways, how we can say that our clinical pathway can be shared with other people is how much of this terminology, which is the standard terminology, we are using in our clinical pathway. So sometimes you cannot encode everything. So you use some global terminology and use some local terminology if you cannot find it in SNOMED-CT. So, but the best clinical pathway is the one that is adopting most of these international terms so that it can be exported easily to other clinics and other practitioners in order to be used. So here we are just showing some of the measures that allows us to measure the conformance and standardization, how standard is our clinical pathway, the conformance of the clinical pathway, and the classification of clinical pathway terms. So, and then clinical pathways are encoded using SNOMED-CT. This is a SNOMED-CT term that describes the ischemic stroke. And then when you say to the nurse, okay, take the patient and give him an X-ray, So that X-ray is, the details of the X-ray are entered in the EMR. But they are not entered in the EMR as part of being treated for ischemic stroke. Because we know that. I'm sending him because he's in the neurology department. But in the EMR system, after a while, if I want to go and see the government or the healthcare institution at the regional level, they want to know how many X-rays we have done to patient who has been admitted with ischemic stroke. It's very difficult to get this information from the EMR because the act is not linked to the disease that the patient is coming from. In order to do that, you have to open the file and read it and see who's the patient, who's the doctor who asked for that. Oh, this doctor, he's a neurologist. Then maybe he asked for this act because of the clinical ischemic stroke. But if I want to do it in a mass using big data, I need to link these two together. So what we do, whenever we ask for an act, we link it to the CT, to the SNOMED CT code of the disease that we acted on. And this is the way we are doing this. So on the left-hand side, you have the SNOMED CT of the disease. On the right side, you have the SNOMED CT of the act. And then we link them together. And here we're showing some CP analysis conformance to the treatment to know exactly how good was the treatment in terms of, for example, if I want to know the CP blood test, and I want to see the rate of how often we are asking for this blood test and so on. And here we're showing the overall architecture of the system. And here we're showing some of the way we encode this using Semantic Web. And then this is some of the snapshots of the overall architecture. So encoding here some business rules. And then here's the overall architecture of the system. And then the proximity based, which is we're doing some big data analytics on the data that we collected here. And then we're showing the overall architecture of the system. And the conclusion here is to say that ontology and semantic web is a perfect platform to clean the data, select the data, discover it, which is selection, clean it, link it, pre-process it, get it ready for big data analytics because of everything that I mentioned earlier. So connecting, it allows you to connect all this knowledge together and then be able to share it properly. And scaling ontology, which means that if all the hospitals are using these ontologies and the data can be made available and exchanged, so this could be a very good platform for global health issues, to treat global health issues. And this comes to end of my presentation, and thank you very much for listening.